Hello and welcome. For this video we are looking at atoms and radiation, in particular radioactive decay for the higher tier, and we're going to be learning how to do something called nuclear equations. Okay, now in order to work this out we're going to do this for alpha decay and for beta decay, so we're going to look at the changes in the nucleus that happen if an atom decays by alpha radiation and by beta radiation. And the first example I've got here is the nucleus of a substance called thorium. Now you're not required to remember the names of the atoms and elements and the names of the atoms and elements they change into. What you are required to do is be able to describe the changes that happen in the nucleus as a result of alpha decay and beta decay. Gamma decay doesn't cause any changes in the nucleus other than the emission of gamma radiation, so we don't need to look at that. Now here's an example of an element called thorium, and this is just the nucleus of the element thorium. There's no electrons or electron shells shown here. Radioactivity is only given out by the nucleus, and for thorium we have a mass number of 228 and we have a proton or atomic number of 90. Now it's important to remember here that the mass number tells us the number of protons plus the number of neutrons, so if we add the protons and the neutrons together we'll get the mass number, and this number here called the atomic number or the proton number tells us the number of protons. If that's all a little bit unfamiliar and confusing, you might want to look at the video on atomic structure that's already been made. Now the reddy sort of pink coloured circles here are the protons and the green ones are the neutrons. Now imagine this substance was to give out a particle of alpha radiation. Now if you've watched the previous videos on radiation, you'll know that an alpha particle is made up of 2 protons and 2 neutrons. So if we look at our key, here are our protons with a positive charge each, and here are our neutrons with no charge on them. Now if that has ejected or been ejected from the nucleus, that means the number of protons plus neutrons must change and the number of protons must change, because we've lost 2 protons and we've lost 2 neutrons as well. So how does it change? Well, if the mass number is protons plus neutrons, here I've got protons plus neutrons equals 4. If I add the protons and neutrons together, so that means that number changes by 4, and because they've been lost it goes down by 4. It becomes 2, 2, 4. The proton number is 90, but if I've ejected an alpha particle I have lost 2 protons, so that number becomes less by 2, so that number becomes 88. And remember, if you change the proton number, or if there is a different proton number from an element, it's no longer the element that it was before, it's a brand new element. So in this case the element is radium. It's an element called radium, so this actually has become a brand new or different element. So what we end up with is, we started with thorium 22890, we now have 22488, and we have our alpha particle. An alpha particle can be written like this, and we have to write down the number 4 at the top there and 2 at the bottom there to show 2 protons, and here to show a mass number of 4, protons plus neutrons of 4, and that's been lost. So there is our nuclear equation for the decay of a thorium nucleus by decaying by an alpha particle. Okay, the next one we want to look at is a decay by a beta particle, and this is slightly more complicated, because what happens with beta decay is we have a neutron which will change into a proton and an electron, and that electron shoots off as the beta particle, and we have a neutron left that has been converted into a proton. So that means the proton number will go up by 1 because we have 1 extra proton. The neutron number will go down by 1, but the mass number doesn't change. The mass number stays the same, because mass number, remember, means protons plus neutrons, and if you just convert a proton into a neutron, that means the mass number doesn't change, because we're not adding or taking away from the total. Okay, so here we have potassium, and it has a proton number of 19 and a mass number of 40. This is a radioactive isotope and it gives off a beta particle. So imagine, let's have a look at this one here. Let's pretend this neutron here is where it's going to happen. Remember, we can't predict which atom radiation is going to happen from, but let's just, for this example, say it's this one here. What we know is a neutron changes into a proton and an electron. So if that was the neutron we were looking at, this is what would happen. You can see that the neutron there has converted into a proton, and here's our electron, and that electron zips off, shoots off at very high speed as our beta particle. Okay, so how do we write a nuclear equation for that? Well, this is how we do it. We have the potassium atom there, and if we have lost a beta particle, that means a neutron converts into a proton, so that proton number is going to be one more because we've got another proton. The mass number doesn't change because mass number means protons plus neutrons, and all we've done is converted a neutron into a proton, so that number stays the same. So what we have is two new numbers. We have 20 on the bottom, and the number at the top stays the same. That means if we've got a different number of protons, that is a different element, and in actual fact that element is calcium. Okay, but we've got the change into the atom of calcium plus a beta particle which is ejected. A beta particle, for the mass number we would write 0 because it has no mass. Proton, you might equate this to the proton number, but what we actually write is the relative charge. So this is an electron, so it has a charge of -1. So this is slightly more tricky to remember, but just remember there's no mass and we have a charge of a -1 for our beta particle. So this is the nuclear equation for the decay of a potassium atom by a beta particle. Now you might need to go over these two slides once again just to make sure you understand, and once you're fairly clear on that, let's have a look at a couple of examples. So here are a couple of examples. If you would like to, you can pause the video here and try these for yourself and see if you get the answers right. If not, you can just continue and see what the answers are. So for our first example, we have uranium-235 with a proton number of 92. It decays by an alpha particle and it becomes the element thorium. So we want to know what the new atomic mass is and what the new atomic number is. So we have lost an alpha particle. So remember, the details about that are it loses 2 protons and 2 neutrons. That means the mass will be less by 4 and the proton number will be less by 2. So if we take away 2 from there, that gives us 90, and if we take away 4 from there, that gives us 2, 3, 1. So the numbers that go in here are 90 and 2, 3, 1, and it's already told us which element that becomes. And here's our alpha particle which has been ejected and shoots away. Now for the copper, we have an atomic mass of 64 and a proton number of 29. What happens there? Well, remember, there's no change in the mass, but a neutron becomes a proton and an electron. So that means we have one extra proton. That results in an extra proton and an electron, and the electron is gone. Remember, that's given off as a beta particle. So we have one more proton, but no change in the mass. So if we have one more proton, that goes from 29 to 30, and there's no change in the mass, so that stays at 64. And the atomic number that corresponds to an element is zinc, so zinc has 30 protons, so it now becomes zinc plus our beta particle here, which we say has a -1 in terms of its relative charge and a 0 in terms of its mass. Okay, so hopefully that made some level of sense. You might need to go over this once or twice and maybe try a couple of practice questions out of your book or that you might get from your teacher, but other than that, that's me done. Thanks for watching, and I'll see you again soon.